Hello friends, moving on to the next question. The increase in width of the depletion region in a PN junction diode is due to. It's a direct NCERT statement that I'll show you. So you could see here a PN junction under reverse bias, PN junction under forward bias. So for PN junction under reverse bias, the depletion region widens due to change in electric field. And for PN junction diode under forward bias, the depletion layer width decreases. So it's a direct statement from NCERT. For reverse bias only, there is an increase in width of depletion region. Next question, light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. Whenever a frequency greater than the threshold frequency is incident on a material, sure there is going to be photoelectric current. When what will be the photoelectric current if the frequency is halved and intensity is doubled? We know that photoelectric current is directly proportional to intensity. If the frequency is halved, if the condition frequency is halved is not given, you can directly go to the statement doubled, because photoelectric current is directly proportional to intensity and the frequency is greater than threshold frequency. If I am going to consider the condition frequency is halved, 1.5 times the threshold frequency is given. When this frequency is getting halved, you will get 0.75 times nu naught, which is actually less than the threshold frequency. So when a frequency lesser than the threshold frequency is used for photoelectric emission, there will be no photoelectric emission. So for a given photosensitive material, there exists a certain minimum cutoff frequency of the incident radiation called the threshold frequency, below which no emission of photoelectrons takes place. So the answer is 0. So next, assume that light of wavelength 600 nanometer is coming from a star. The limit of resolution of telescope. I'm going to show you a direct example question from NCERT for this. It's obvious that solving NCERT exercises and examples could fetch you a great mark than not solving. So you could see here, assume that a light of wavelength 6000 Armstrong coming from a star. What is the limit of resolution of telescope whose objective has a diameter of 100 inch? So the same question, diameter is provided, the wavelength is provided. Just use the formula given. Del theta, which we call it as angle of resolution or simply resolution whenever possible, is equal to 0.61 times lambda by a, where lambda is the wavelength and a is the diameter or radius, or you can add 2a in here. So 2a divided by 2, meaning diameter divided by 2, radius of the telescope must be considered. 0.61 lambda by a, where a stands for radius of the telescope, not diameter. Next question. So a ray is incident at an angle of incidence I on one surface of a prism, of small angle prism. It's given that it's a small angle prism and emerges normally from the opposite surface. So there is a prism, a ray is incident at an angle of incidence I. Consider the normal. So a ray is incident at an angle of incidence I on surface of a small angle prism with angle of prism A. It is also given that angle of prism is A. Emerges normally from the opposite surface. So if it emerges normally from the opposite surface, angle of emergence is going to be 0. This is because the angle of emergence is the angle made between the normal and the emerged ray. So when the emergent ray and the normal both coincide, the angle between them is going to be 0. So for normal emergence, E is equal to 0. For E equal to 90, the kind of emergence is called grazing emergence. So it will go in this way. This is called grazing emergence. This is normal emergence and this is grazing emergence, and for grazing emergence E equal to 90 degree. Emerges normally from the opposite surface, it is given E equal to 0. If the refractive index of the material of the prism is mu, then the angle of incidence is nearly equal to. So you have to find I. I is question. So in order to find this, first I'll show you certain formulas that we are going to use. So for prism you can use R1 plus R2 equal to A, delta equal to I plus E minus A, or we can even use Snell's law, which is mu1 sine 1 sine I is equal to mu sine R1, and I'm going to use it for this surface for prism, for light coming out of prism. So for prism the angle of incidence is going to be R2, since the light ray bends like this and the angle made with the normal is going to be R2. Actually it emerges in this way since it's a small angle prism. So there are slight modifications for this. So mu sine R2 equal to, after the light emerges from light emerges out of the prism, it is going to be air, which I consider to have 1 refractive index 1, and sine E sine 0, which is 0. So mu cannot be 0, it indicates that sine R2 is 0. Sine R2 is 0 indicates R2 equal to 0. When R2 equal to 0, A equal to R1 plus R2, R2 equal to 0, A equal to R1. So what we can do is apply this for the first interface. So 1 into sine I is equal to mu into sine R1. Sine R1, since R1 equal to A, just you can write sine A. So to be clear, I will write it over here for the first interface. So the first medium involved is air. Light ray comes from air, making an angle of incidence sine I, which is equal to mu times sine R1. Since the angle made by the normal with the ray, refracted ray, is R1, I am taking R1 here. And we have already proved that A equal to R1 plus R2 and R2 equal to 0 for the second interface. Since R2 equal to 0, A equal to R1 plus R2, A equal to R1. So you can write A instead of R1. So sine I equal to mu into sine A. So it is also given that all these are small angle prisms. For small angle prism, you can neglect sine as I itself. Sine I is approximated to be I. Mu into sine A is approximated to be A, just A. So angle of incidence I equal to mu A. Also remember, when sine I, for I much less, it's going to be I. For cos I much, that is, well, when the value is very low, cos is going to be 1. For tan I, when the value is too low, it's going to be I again. Only for cos it's going to be 1. Thank you friends.